Hello, ladies and gentlemen. My name is Osnir, and today we're gonna read another article from my Introduction to Academic Driving book. Welcome to my reading room, to my old-timer Mazda, which is over there and here somewhere in my heart and on my t-shirt. So, today's article gonna combine music, mathematics, and astrophysics. You would ask, how is it possible to combine all the things? Come on. The history of humankind proved that it is possible. And let us dive into the topic. So today, I'm gonna read you the article, which is called Music of Internal Combustion. Your car is a musical instrument in a symphony of the universe. If you had to choose between buying the Jaguar F-Type 5.0-liter V8 or the Dodge Viper 8.4-liter V10, you would probably go for the first one. The Viper's odd-firing V10 may be powerful, but, well, sounds silly. If you owned Lamborghini Huracan Performante with a staggering 5.2-liter V10, you would probably enjoy rushing through tunnels and listening to the music of exhaust. Because why would you deprive yourself and people around you of this kind of well-tuned satisfaction? Speaking of exhausts, let me cite my friend Patricia Pedrosa, who stated in the Motor Muses blog that exhaust, which sounds in sol diez tonality, ruins cars. Quote, "It's not a good note. It's feeble. It is not as grounded as C or regular old G. Neither it is as inspiring as A or B. Definitely not as thoughtful as and intimate as the E. That's because G sharp is a weak note. It reminds me of delicate, fragile things. So obviously, having the exhaust note being a G sharp automatically makes the car fragile." End quote. What I'm trying to start this article with, is an assumption that every car is a musical instrument. Every internal combustion engine generates a series of controlled explosions in its cylinders. These explosions not only move the vehicle forward, but emit a series of harmonic sounds. I say harmonic here because explosions reoccur at very precise moments in time, keeping their rhythm and beat. They are mathematically engineered. In turn, petrol fumes are vacuumed away from the cylinders with hissing sounds in no less precise moments. Then there is the constantly rotating crankshaft. All this makes the engine sound like a miniature chemical-mechanical orchestra, with the exhaust pipe functioning as, well, the orchestra pit. Moving further than that, it is not only about the engine. The sound of winking indicators or turn signals also have their rhythm and beat. Sometimes, caught on lights with indicators on, your fingers may start tapping a random melody on the steering wheel. Your consciousness may start singing, simply because you fall under the magic of winking indicators. And this is what you are encouraged to do. By the way, have you ever noticed how the winking of your indicators interferes with an engine murmuring at idle? Now you will. Then there is the sound of tires, which whisper on the asphalt as they move. Different whispers in different weather. Different whispers at different speeds. Or absence of any whispers if you drive a Rolls-Royce Ghost 2. In the latter, however, you will constantly hear the in-dash clock ticking. Then there is the vibrating sound of wind, which tries to break through your window seals. Or noble squeaks in an old classic, which are most satisfactory to hear. The same squeaks in a new car make you feel disappointed and irritated. However, It was your choice to buy the Hyundai's Veloster, wasn't it? In a word, the car is not only about proper driving. It is not only about proper looking. It is also about proper sounding. The car is a mechanically, electrically, and chemically tuned musical instrument which produces hundreds of harmonic sounds per second because it is so precise. All combustion chamber explosions, crankshaft rotations, cooling liquid flows, in-battery gurgling reactions, shifts of gears in a gearbox, and many other noisy processes are mathematically calculated. They happen in strict frequency and continuity. Math makes the music. Math makes harmony. Therefore, just as you hear a discordant sound one day, be aware something is wrong with your car. The alternator belt should not scream in rainy weather. The engine sound should not suffocate on a cold start. The parcel shelf should not rattle. Never doubt it, the car is a musical instrument. Do not forget to keep it tuned and make it sound properly. Always. Actually, everything around us should be properly tuned. Looking far back into history, the ancient Greeks concluded that the whole observable universe was full of euphonious sounds. This was called the Musica Universalis, according to the later Roman interpretation, or the harmony of the spheres. In a nutshell, while moving around their orbits, the sun, moon, and more distant planets emitted sounds. This was inevitable as planets differed in size, mass, and alienation from the Earth. There could exist no disharmony, as this would destroy the whole universe in one big discord. Also, the Musica Universalis could not be heard by a human ear, but as calculated by ancients, it was supposed to exist mathematically. Thus, it should be believed. In this light, the logic of Pythagoras is exemplary. First, he looked at the relationship between the pitch of the musical note and the length of the string which produces it. He calculated this relationship precisely and noted it down in integers: 1 to 2, 1 to 3, 1 to 8, etc. Then he looked at the sky and noted down the observable distances between planets. He presumed that these distances may serve as some kind of strings. At the very end, Pythagoras suggested that the sun, the moon, and all the planets produce their own unique hum, moving around their orbits. He also suggested that the Earth would emit super powerful tenor sounds unheard by any creature living on the planet. Later on, Plato, in his book The Republic, presented the concept of Musica Universalis on paper for the first time. He wrote that this musica emerges from an interaction between 8 celestial levels: the starry sky, Saturn, Jupiter, Mars, Mercury, Venus, the Sun, and the Moon. The first level of this list emits the highest tones. The last emits the lowest. And this is exactly where the contemporary octave system comes from. Notes from Do to C, or from C to B. Plato also concluded that astronomy and music were twinned sciences. Astronomy for eyes, music for the ears, and both requiring knowledge of numerical proportions. Aristotle arrived with another assumption. He pointed out that everything has some weight, and when on the move, produces noises. For instance, running man, flying stone, spinning wheel, striking hammer, etc. Therefore, planets should produce noises as they are very heavy and constantly moving bodies. These noises should be immensely loud. These noises should also be harmonic, as they are consonant to the speeds of planets and distances between them. Finally, these noises can be expressed through proportions between integers. The iron law of unity of music, mathematics, and astronomy, as developed by ancient Greeks, had an enormous influence on our civilization. In the best medieval schools, students had to learn arithmetic, geometry, music, and astronomy as one block of modules called quadrivium. On successful completion, they progressed to the trivium block, which included grammar, logic, and rhetoric. The paradox is that these two blocks constitute the backbone for higher education today. Ancient Greeks, with their philosophy, stand behind the way we continue to live and think. By the way, speaking of today, the original Musica Universalis might have been forgotten, as planets were not observed singing on the move. This does not mean, however, that the whole idea became completely irrelevant. And here comes the moment to introduce an orbital resonance. To begin with, the orbital resonance is not about sound waves, but gravitational interactions. It happens when two smaller planets orbit one bigger planet, usually a star, in a specific reoccurring pattern. For instance, Neptune and Pluto. Every 2 full rounds Pluto makes around the Sun, Neptune does exactly 3. This movement can be expressed in 2 to 3 proportion. What it means is that on its every second round, Pluto is influenced by the gravity of Neptune in the same way as Neptune is influenced by Pluto's gravity every third round. Each of these influences changes the orbits of the planets. It's recoverable in this case. Here you have another illustration, which is hopefully more explanatory. Imagine you put a heavy stone on the seat of a swing. You push the stone until it starts orbiting the linchpin of the swing. With time, both the stone and the linchpin arrive at their optimal and natural frequency and velocity. But you continue pushing the seat, making the stone go faster and faster and faster until eventually the swing gets broken. Now imagine that the linchpin is the sun. The stone is the planet. They orbit one another and everything seems to be fine when suddenly, out of nowhere, a powerful source of gravity comes into play. For instance, from another planet. That is what your pushing means. On every rotation of the planet, you accelerate it against the sun. This happens precisely at the same moment of time and in the same orbital position of the planet. This happens up to the point when the planet crashes away from its orbit. Or it may not if you don't push too hard. There are a couple of very interesting orbital resonances in our solar system. Paradoxically, Neptune is one of the biggest troublemakers. Apart from 2 to 3 to Pluto, it frequently resonates in 3 to 5, 4 to 7, and 1 to 2 proportions to other bodies. It also resonates in 2 to 5, 3 to 4, 4 to 5, 1 to 4, 1 to 5, 1 to 3, 3 to 7, and even 6 to 11 proportions, but very rarely. If you turn your imagination on and assign Neptune with a unique sound on every resonance, you will end up with some kind of a melody. The most famous and exemplary orbital resonance, however, is the one called Laplace. It is the 1 to 2 to 4 resonance of Io, Europa, and Ganymede, the 3 moons of Jupiter. In other words, you have 4 celestial bodies, planets, sending their gravitational waves to one another in a mathematically precise order. The 1 to 2 to 4 rhythm and beat are apparent and, well, appalling. Laplace resonance became possible due to the gravitational pull of Io in Europe, which coupled with the one from Jupiter and trapped Ganymede into Jupiter's orbit. Otherwise, Ganymede would probably disappear in the dangerous depth of unknown space. Continuing with Jupiter's trickery, it resonates in proportion 1 to 2 to Saturn. Because of this clash of the solar system giants, scientists speculate that a huge gravitational push was created a long time ago, which propelled both Uranus and Neptune into their higher orbits. Because of this push, actually, Neptune is now cold and alienated from the Sun. You may ask now, mates, what is the point? Why have you written so many words, Ost? My answer is, well, simple. Do not break wind in your car. You will disrupt the harmony of the universe. Ladies and gentlemen, thank you for being with me today. I hope you like this combination of music, mathematics, and astrophysics. And if you do, consider subscribing. Consider having a look at my videos over there. And also consider having a look at my books. Links in the description. See you next time. Thanks for being with me.